Right, that's right. Hi everyone, can you see my screen okay?
Yep.
Perfect, thank you. So I know I'm standing between you and conference dinner, so I promise I'll be as quick as I can. So my name is Alex Chaushev. I'm a postdoc at UC Irvine. I'm working in SCExAO's group, and the group is primarily interested in high angular resolution imaging with things like masking and kernel phase, the latter of which I'll be talking to you today. So we've been doing kernel phase with the CHARIS instrument. CHARIS is an IFS, which sits behind SCExAO on the Subaru telescope. And we've been interested in using CHARIS to search for signs of accreting protoplanets. So just to briefly mention the science case, one of the reasons we're interested in accreting protoplanets is because they give us a lot of information about the planet formation process, both from trying to characterize their atmospheres and continuum emission, but also for looking directly for signs of accretion using things like, by looking for things like the H-alpha lines. Yeah. So a really good example of this is the PDS-70B system. I have some plots here from Haffert et al., where they found H-alpha line emission. And by looking for these line emissions, we can put a concrete timescale on or we can put a timescale on the formation process of these planets, which is really, really cool and helps to constrain planet formation theories. Aside from H-alpha, there are some other emission lines that we can look for. In particular, we're interested in bracket gamma. Now, there's a really nice paper from Aoma et al. Where they model the relative strengths of these different lines, and bracket gamma is significantly fainter than H-alpha. However, when we take into account the extinction effects that affect H-alpha, we sort of come up even and still reckon that bracket gamma is a very interesting accretion tracer to go after for these young planetary systems. Of course, finding such planets within or close to the host star is very challenging, especially when you get below 3 lambda over d. But the planets that are close to the host stars are also some of the most scientifically interesting. And so this kind of motivates us to think about different ways of doing this and pushing past conventional imaging techniques, which brings us around to using kernel phase to do this. So for those of you who don't know, just a very brief primer on kernel phase. The idea behind kernel phase is that we can model our conventional telescope as a spherometric array. And in doing so, we can improve the performance of our data, particularly below 3 lambda over d. And we can get too close to and beyond lambda over d when detecting new companions. So the first step for kernel phase is that we take our model and we discretize it. And what we can do with this discretized model is, in the case where we have a very small wavefront error, so if the AO system is performing well, or if we're in space, we can link the pupil phases to those phases that we measure in the actual images. And by doing this, we can then begin to, by doing this link, we can then start modeling the pupil array. Right, we can then start to construct some baselines using these virtual pupils. And when we construct these baselines, we can then model this in a relatively simple way, which is that we can set up an equation which links these baselines to these measured UV plane points. And that's given by our A matrix. One difference between kernel phase and something like closure phase is that we have redundant numbers of baselines, and this is incorporated in our redundancy matrix. And then we can basically try and find a kernel phase matrix K such that K cancels this term and leaves us just with our science phases, or in this case, K times the science phases. And once we do this, we can then take this new interferometric observable and we can use it to do our model fitting. So just a little bit more about the CHARIS IFS observations that we did. So we were observing in high-res K-band mode to try and do this kernel phase work. This covers roughly around from 2 to 2.4 microns with 17 different spectral channels. We ended up with 3 different pointings for 3 objects: a PSF calibrator, a telluric calibrator, and a known binary. And our goal with doing these observations was to recover the known binary. And so for each of these, we ended up with varying number of data cubes, somewhere between 42 and 58. And each data cube consists of one exposure of 20 seconds covering 17 different spectral channels. So for each data cube, we have 17 different images. So one thing that is great about kernel phase is that it's a linear model, which to some degree means that, to third order means that a lot of the aberrations in the wavefront in the phase errors are cancelled out. But nevertheless, that there are some systematic errors that propagate through to the kernel phases. And typically this is what ends up limiting kernel phase observations. So they're not noise limited, we're limited by residual systematic errors driven by all kinds of things to do with the AO system and the particular observations that we're doing. One way to mitigate these residual systematics is to subtract off kernel phases from a reference PSF calibration star, one which we know is unresolved and is not a binary. And in doing so, we can mitigate some of these errors. One thing that's nice about observing with an IFS is that we have a lot of images which are taken at the exact same time in adjacent wavelength bands. And this allows us to do a kind of spectral differential imaging kernel phase calibration as opposed to the reference differential imaging, which is typically done. And there's a number of reasons why we think this might be better. So first of all, the observations are done, the way the data cube is taken at the same time, so there's no short-term temporal variations. There's no differences in air mass between the science target and the calibration star, and there's also no difference in spectral type. And all of these things mean that theoretically we should be able to do a better calibration, particularly for the science case that we're interested in, which is for looking for line emission from one particular spectral bin. So this is a kernel phase fit of our low contrast binary data, HD 44927. So the plot on the right shows the measurable kernel phases in the x-axis and the model kernel phases on the y-axis for 4 of the spectral bins. You can see there's a really strong one-to-one correspondence, which means that we successfully recovered this binary, which is great. This plot here, the bottom plot, shows the residuals after subtracting the model, and we can just see that they're consistent with those of the unresolved PSF and telluric calibrators. And this is great because I think we've tried to have a look through the literature, but I think this is maybe the first time that someone has done kernel phase with an IFS. I'm happy to be corrected on that if I'm wrong. But it demonstrates that we are able to actually use kernel phase from the ground using CHARIS. So going back to our question of calibration and of improving the performance of kernel phase and removing these systematic errors, one way to consider how well we can do this between SDI versus RDI is to look at the correlation coefficients between the different spectral bins. The left figure shows the correlations between each of the 17 spectral bins for the PSF data, and the right figure shows the correlations between the PSF and the telluric. And what we can see is that the telluric, the average correlation ends up being around 0.83. The average for the PSF varies quite a bit between 0.27 and 0.99. But if we consider only the top 3 most correlated spectral bins for each band, then we end up with something like 0.92, which is slightly better than the RDI style calibration. And so for our data analysis based on this, we decided to adopt a very simple SDI scheme where we subtract 0.5 times the kernel phase of the band below and 0.5 times the kernel phase of the band above for each spectral bin that we're interested in. And this was the key result plot of this analysis. So the figure on the right-hand side is a contrast curve plot showing the performance of SDI kernel phase with the contours and the RDI kernel phase with the dashed black line. So the y-axis is increasing contrast of the tentative injected companion, and the x-axis gives us the separation of that companion as well. So overall, by doing this simple SDI correction, we gain somewhere between 0.3 to 0.4 magnitudes in contrast over RDI, which is fantastic and a very, very good start, because the technique that we used is very, very simple. And of course, there's more sophisticated techniques which could improve on this potentially further. But again, it's a good proof of concept and shows the kind of performance that we can achieve. So I should note that this is just taken for, this contrast curve is for 20 minutes of data. We reckon that we can probably significantly improve the performance for observations for half a night. So finally, I have a plot of some potential future targets that we could follow up using CHARIS. There's some limits that we have to consider. So the wavefront sensor operates in R band, and magnitudes of R, and the R magnitude has to be brighter than 8 to be considered in the high performance parameter space for SCExAO. We're observing primarily in K band, and just to note that we have a K band limit of 5.5 for CHARIS where it saturates. There is an option of using a beam splitter, which gives us a little bit more wiggle room in terms of observing brighter targets. But in general, the parameter space that we can potentially observe in is fairly limited, since most of our targets are fairly brighter in K than they are in R, sort of squeezing us in between those two limits a little bit. However, we have submitted a science proposal for a target at R 9.5 to try and understand whether observing fainter targets will significantly degrade the performance of the kernel phase results. And that's it. So we've been able to perform kernel phase from the ground using CHARIS, and we can, there's some promising indications that using SDI as opposed to an RDI calibration will help improve on the current systematic flow for kernel phase analysis. And there'll be a pipeline and paper coming soon. Thank you.
Thank you. Any questions? Looking around, I think everybody must be thinking of the conference dinner already.
Sure, sounds good.
Check the chat. Okay, well then, thanks again.